Hi guys, so let's see 13.2 colored complexes. Now usually compounds of group 1, 2 and 3 are white as well as zinc because it's not classified as a transition element, and transition elements have the characteristic property of forming brightly colored compounds, and that color is because of partially filled d orbital. So copper 2 plus has a partially filled d orbital, so that's going to be colored, but Zn2 plus has a completely filled d orbital. That's not going to be colored, that's going to be white. So you'll have the coordination number that you will complete. Just leave out the shape, leave this one out, we haven't done shape yet. So here coordination number is 6. Here is 6, 4, 2, 6, 6, and 4 plus 2, that's 6. And the oxidation state on the metal ion, so water is neutral, so F is going to be 3 plus, Cn minus, so you'll have to calculate it. So 3 plus. Here Cl is Cl minus, so calculate. And here 2 plus. Ammonia is neutral, so it's going to be Ag plus. H2O is neutral, so CO2 plus. Neutral, Cu2 plus. Here both of them are neutral, so it's Cu2 plus. There you go. Now, let's see how we explain the color. So usually the metal will have all the 5 d orbitals on the same energy level as here, and because of they are of the same energy level, they are called degenerate d orbitals, so they are of equal energy. But as the ligand is going to approach, so when the ligand approaches, the ligand is going to cause the d orbitals to split. So now the d orbitals are said to be non-degenerate d orbitals, and we said that there is d splitting. So there is splitting of the d orbitals when the ligand approaches. So then you have 3 d orbitals at the lower energy and 2 d orbitals at higher energy. So what happens is that in the lower energy, you will have electrons. So let's say you have, so when you're filling in, you'll be filling in paired single electrons first, and then you'll be pairing up. So let's say it's like this. And if you have one electron that is going to absorb light, so this is going to absorb light, and when it absorbs light, it's going to be promoted to the d orbital of higher energy. So as it gets promoted, so we say that it gets excited. So this is going to get excited, absorbs energy, gets excited to the higher level, and eventually it will fall back. So as it's falling back to its initial level, it will release light of a specific energy corresponding to that orbital splitting. So depending on the splitting here, on that delta E, depending on the splitting, you will have a certain wavelength of energy that is released that is going to affect the color. Right, so let's take for example Cu2 plus. So 3d9, so let's have the degenerate d orbitals. So we fill in singly first, then we pair up. Now because of the Cl ligand, so the Cl ligand is going to cause the splitting of the d orbitals. So this is going to split. So you will have the non-degenerative d orbitals, 3 at the bottom, 2 at the top, and we will fill in the electrons. Again, we'll fill in singly first, so 1, 2, 3, 4, 5, and then we'll pair up 3 and 4 like that. And between the two energy levels, you will have a certain delta E. Now, what is going to happen is that as this is exposed to light, so one electron is going to absorb light of a specific wavelength and is going to get promoted and get excited to the higher energy level. So as it gets excited, so it's going to move from here to here. Okay, so it gets excited and eventually it will fall back to its energy level, to its initial level. So as it's falling back here, it's going to release light of a specific wavelength, and as it releases light, it's going to cause this to be colored. So CuCl42-, this is of a yellow color, and if something is of a specific color, it means that yellow color is being reflected. So means that CuCl2 is reflecting the yellow color. So this is reflected. This is why it's yellow. So this is the color wheel. This is going to help you to guide to know which color is reflected and which color is absorbed. So this is reflected, yellow color is reflected because the purple color is absorbed. So the complementary color to yellow is purple. So this purple color is absorbed. So when light of purple color is absorbed by that electron, it gets promoted and it's going to get excited. So this is purple color is going to cause that electron to get excited, and as it gets back to its ground state, so this is going to release yellow color. So yellow color is reflected and purple color is going to be absorbed. So you can read through this. This explains the color. Now, any factor that will increase or decrease that delta is going to alter the color. So that delta is going to give us the color. So the more it is, we'll have more energy gap. So it's going to affect the wavelength. So the factors that affect the delta E is the identity of the transition metal, the ligand, and the oxidation state of the transition metal. So metals, usually down the D block group, so down each group, the delta E is going to increase down the group. So as you can see, cobalt, rhodium, and iridium here, the splitting is increasing. So if energy is increasing, energy is inversely proportional to wavelength. If energy is increasing, wavelength is going to decrease. So the more the splitting, the less the wavelength of the light. So splitting increases down the group for the same oxidation state. So all of them here are in the 3+ oxidation state, and delta E is increasing down the group. Now, as the oxidation state of the metal increases, so metal becomes more charged and is able to attract the ligands more. The closer the ligands are to the metal, the more there's going to be interaction between the metal and the ligand orbitals. Therefore, there's going to be more splitting. So when the charge of the metal increases, the splitting increases as well, because the ligand is going to get closer to the metal. The third factor is the identity of the ligand. So in section 15 of the data booklet, you will have the strength of the ligands. So we have weak field ligands and strong field ligands. Normally, weak field ligands, they cause smaller splitting. Strong field ligands, they cause more splitting. Now, when you have copper sulfate, so hydrated copper sulfate is blue, and if you add ammonia to this, it changes from pale blue to deep blue. So initially, this is blue color because of the H2O ligands. So H2O ligands compared to ammonia, H2O are is a weaker field ligand, and when you add ammonia to it, the ammonia is going to replace the water ligand. So as it replaces it, because ammonia is a stronger field ligand, it's going to cause the increase in the DD splitting. More DD splitting means that the energy gap between the D orbitals is going to be more, and then hence the light that is going to be absorbed is going to be of shorter wavelength. So this is why you have that change in color. It's because of the replacement of the ligands. Now, the color wheel is a very important tool for you to know the color of the complex. Now, depending on the color absorbed will depend, of course, on the DD splitting. So if you have, here and here. So if you have a small DD splitting, means that the energy required to promote the electron is small. So small energy, remember that E is inversely proportional to wavelength. Small energy means that the wavelength of the light absorbed is high. So light absorbed high wavelength, so that's red color. And this means that if the substance is absorbing red color, it is going to be reflecting light of opposite color. So a red compound, if it's absorbing red color, this is going to reflect the green color. Hence, the compound is going to appear green. So the color that you see is the color that is being reflected. So here, the color of the complex is going to be green. And similarly, if you have large DD splitting means that the wavelength is going to be small, and small wavelength of light absorbed is going to be purple or violet. So let's make that to be purple. So these two, let's put these two to be purple. So it's going to be easier for us. So purple absorbed, which means that the substance is going to be yellow because it will reflect yellow color. Right. So you can complete this table. So this color wheel is available in the data booklet at section 17, and it's going to allow you to be able to predict the color of the complex. So let's see that example. So titanium 3 plus in the presence of water ligand is going to absorb yellow light. So yellow light, hence the complementary color is purple. So if yellow light is absorbed, purple color is going to be reflected. Hence the compound is going to appear purple. We had already discussed about this, is that ligand, because it's a lone pair donor, acts as a Lewis base, and the metal ion, because it accepts the lone pair, is going to act as a Lewis acid. So that's it for unit 13.2. Thank you, and attempt the end of unit.